I'm recording this now, so thanks very much for your time, and I hope you're feeling better, Claire.
Okay, so let's start by sharing our screen. So can everyone see that image with solar imaging up the top?
Yep.
Yeah.
Excellent. All right, well, first we should thank you guys for inviting us, which is fantastic, and apologise for
all the
delays that were things out of our control and not being there in person, but otherwise it's all good. Firstly, we should say we're not experts or anything like an expert. We're just enthusiasts that sort of have been doing this for a bit over a year or more, the solar astronomy. So if you really want some expert advice, these two books, and one oddly enough is about planetary, but a lot of the techniques are very similar, and these two books were written by the same crew of people. They take the word amateur to a whole new level. I believe the solar astronomy one you've got there in your library, is that right? Someone?
Yep.
Yeah. So really, really excellent knowledge there. And hard to beat that sort of information. So those guys are a good go-to place. Before doing anything about solar astronomy, of course, there's always the safety thing. So starting at the top, we're all aware that we get the scopes and it says never, ever, ever look through your scope with the naked eye at the sun. So if we're going to break that rule, so the second rule is only use solar products that are reputable and in accordance with their instructions. So, you know, there is stuff on AliExpress and what have you that you can buy, but I'm pretty sure you don't want to put your eye to the eyepiece. So, you know, don't do that. And in our case, failing 1 and 2, because we have made up our own systems, is that you want to make absolutely certain you know what you're doing before you go looking at it. So if you're not sure, because we're going to show you some things that, you know, on the forums you're not allowed to show them because they're not meeting those safety requirements. Lastly, never test the setup with your eyes. We've got cameras for this, so you know, if you can always replace a new CMOS camera, but your eyes obviously isn't a go, so go with that one. And an admission from us is that we've actually never ever put an eyepiece into any of our scopes to look at the sun. So we only use cameras and the screen, and pretty much that's the case for all of our viewing. So our setup. This picture is showing one of the delays. This was a picture taken a couple of weeks ago when Claire just broke her arm. That's where we sit to do our astronomy, be it night or day. And so we'll come back to some of those things there, but we normally look at that screen to see our images. The scope is sort of just out the door where the sunshine is, not on that little tripod, but a little bit further to the right than that. Okay. Before we go into the talk, I guess the Kelly was very broad and just said, you know, seen your pictures online, you know, do you want to do a talk? So there were only guidelines recently saying that when she thought that we probably had about 500 slides, that she said, well, maybe try and cut it down to a bit of a shorter length. So we will go quickly through a number of things. But the talk is really about what we've done in solar astronomy. So it's just a little bit of a progression of where we started to where we're more or less are now and what things we've made and done along the way. So a little bit about us. We both did maths and science at school. We're both lifelong nerds. Now we're pretty happy with that, being called that. But back when we were kids, the nerd hadn't been invented when we were young, and you were called a dag instead, and that wasn't such a good accolade. But anyway, now we think nerds are pretty cool. We're both at school age during the Apollo era and both have vivid memories of that day in July. And, you know, I remember as a child going out into the street to see the first Sputniks go over and the near panic of the populace about all that. So it was a very impressionable thing that probably has influenced us into astronomy. We've had many and varied interests, mostly around science, engineering and technology, which includes astronomy, but we haven't actually really actively done astronomy until retirement. So if we both on separate occasions before buying our own stuff had seen Saturn, and that was the kicker for both of us, that Saturn was the thing, and so we bought stuff. What have we got there? So when we retired, we didn't retire 4 years ago. It's a lot longer ago than that. But about 4 years ago, it was Claire, in actual fact, that wanted to do astronomy and said, let's buy some equipment and get into it. So, which we did. Just a little bit more on the Apollo stuff, just to show some things which was of interest. That's the colour lift out from the Age. It was one of the only colour ones ever done up until that point of that day. And the card there with Neil Armstrong's signature, I wrote away to NASA to get that. And it sat in a drawer, neglected for 50 years, thinking it was just a mass-produced thing. And then in 2019, for the 50th anniversary, I got that card out, and we saw a documentary that said that Neil Armstrong personally signed every signature that he sent out. There was no printed ones at all. And we checked online, and true, it's different to all the others. They're all different, but they're the same, if you know what I mean. So, and that's a little bit more of the colour lift out there. So there's that. Just quickly, some planetary imaging. This isn't any particular special good ones or anything like this.
But this is where we started out with our story.
November was when Kelly first suggested that we do this talk. So that was that night we made this slide. So there we go. So this was the last planetary season, which was, those people who've done planetary know that seeing was absolutely atrocious for the entire time, and it was pretty hard to get anything. But there's a few things: Neptune, Triton, Uranus, and Mars. We went Mars happy. Those people into planetary know that the planets are leaving us for probably the last time in my lifetime, going to the northern hemisphere. So they're going to be low in the sky for us. So, and back to Luna and the Moon, and of course the lunar landing site. So away we go. So why solar imaging? Why did we do that? We thought that we'd already invested in equipment. So we thought, well, we've already got equipment sitting there. Why not use it? Sitting around on nice sunny days with cloudy nights makes you think about our nearest star. So those of you who have had that wonderful experience of sitting there with a lovely clear day and then the clouds roll in at night know exactly what we're talking about. And solar imaging uses many of the techniques or similar techniques to doing planetary and lunar, which is pretty much what we're into, not so much DSO stuff, which is pretty much the odd one out and doesn't share the same techniques and what have you. It's also coming up to solar maximum. So those people who know the sun has an 11-year cycle. So it's a pretty exciting time on the sun. So it was a good idea. So we did that. And as it turned out, having started doing it, we've found it probably the best astronomy thing that we've ever done. So even beats the planets, maybe just on a good night, depending on the case. So that's what got into it. And so where did we start? A little bit about the sun. Yes, what we're trying to see. This is quick. So the sun emits that wavelengths of electromagnetic radiation there across the bottom. The black line is an idealized, I've got a mouse to show you. Okay, can you see the mouse pointer? Yeah. Yep. So that's the black body curve of what radiation would look like. The yellow is what actually comes out from the sun across all those wavelengths. And the red is what makes it to our surface, because these things are absorbed by our atmosphere. So there's no point looking in some of these spots. And this is the visible bit. So this is the bit that, you know, initially we sort of aim for to look at, but even in here, there's some different things to see. So the next thing shows you the spectra from the sun. So in that, you know, basically visible light, there's all these missing bits, as we know when we send light through a vapor or a plasma. The elements absorb particular wavelengths, and ones of particular interest are the lines labelled C and F, which are due to hydrogen, and hydrogen alpha particularly, which is C over here, is particularly interesting. K and H on here, so these ones over here are the calcium lines, which are also interesting, and D is due to sodium. So that sort of alters a little bit of the equipment you need to see some of these things. So, and what are you actually looking at? So outside here, the corona, up until relatively recent history, the only way to see that was during an eclipse, but now you can have a coronagraph. We're not doing that. And that is a long way out and really, really hot. So a few million degrees Kelvin, and it gets warmer as it goes out, which is something that scientists are still grappling with, because it should obviously get colder. The chromosphere is above the surface, and this is what you can see in HA, and it runs from 500 kilometres out to thousands of kilometres out from the surface. The photosphere is where the majority of the light comes from. So this is the thing that you're going to see most of, and it blots everything else out, and that's from the surface at zero surface, inverted commas, and it is hotter than the chromosphere because it does follow what you would expect, cooling until it gets out here and gets hotter again. And the convection zone underneath is of interest to us because that's some of the stuff that you can see in the photosphere where the convection cells come up and hit the surface. So we're basically going to look at these two of what we look at. So, all right. So where we started, so we had some scopes, so we thought, well, white light images of the photosphere, that would be the simple and easy and cheap thing to do. Another thing we could call this talk is cheap. So we purchased a Mead, thinking it was good quality product, Mead white light glass filter, and these are called full aperture energy rejection filters. And that was for our 72 ED. And then we purchased a Celestron, again, thinking this was a good quality, well-known film filter for our 6-inch SCT. Quick tip, don't do either of these two things because both of those products are utter rubbish, and it was a big learning thing about what supposedly reputable brands are. Don't buy a glass full aperture filter unless you're prepared to spend thousands and thousands of dollars. And the film filters are fine, but not this thing from Celestron. This film is from people who make 3D glasses for theatres, apparently. So having found this out afterwards, could have done the research before buying, would have been a good idea. That's a tip. And we started off with our one-shot colour planetary cameras, an ASI 224 and a 178 MC, which again seemed like a very good idea at the time. But so there's the 72 ED. That's the glass full aperture filter. That's a little thing we laser cut up to find the sun. So it's got a little pinhole there and a crosshair there, so you can very quickly and easily find the sun. That's our 6SE, and that's the Celestron thing, and that is one of those two cameras, either the 178 or the 224, directly plugged into it. So first attempts out of that. So that would be the 72 ED. This would be the 6SE, and this is some of what you could get with those filters. These colours are straight out of the camera. So this is what you would see in colours if you put your eye to it. these aren't false colours or anything because they are a colour camera. So that was the starting point, and that got us hooked and made us spend silly amounts of money that we hadn't anticipated on wanting to spend. But anyway, so we needed more stuff. The first thing we did is, remember that idea that we had the equipment? That was wrong. So the first thing is we changed to a monochrome camera. We'll come to that in a second if those people aren't quite aware. But if you're only looking at a one wavelength of light, a colour camera isn't particularly useful to you. And we changed to beta solar, the beta solar continuum filter of 450 nanometers, which is 540 nanometers, sorry, is about 7 nanometers wide, and it helps the contrast in those white light images. So not super expensive for that. We replaced the 2 white light filters with DIY filters made with beta Astro safety film, neutral density 5. If you're going to do anything, buy that stuff. That you would, good. Yeah, it's sensational. It is, we won't mention a Herschel wedge here. You can buy a Herschel wedge, but to all accounts, this stuff is as close to a Herschel wedge these days as you can get. And the change of just changing that film was astounding. We'll come in a minute. If you use the 5, you're meant to be able to put your eye to the eyepiece. So it's meant to cut out 99.99, I think, or maybe 2 more nines after that % of the light. So it's pretty safe to use. So we 3D printed some brackets and laser cut some discs and just clamped the film. Do not clamp the film tightly. If it's saggy and baggy, it's the better. So it's all got to do, there's a lot of physics about wave fronts and everything, but it doesn't upset it. If you stretch the film, you destroy its optical quality. So so we just put that out on a table and had the disc here with some double-sided tape on it and just dropped it onto the top of it. So there was no tension whatsoever. All right. This is very quick. I could explain this in a lot more detail, but a monochrome camera, this is a pretend 16 pixel camera. So we've got 16 pixels in monochrome, you get all 16 pixels. And if you get a 16 pixel color camera, there is a color mask over the top of them. And in actual fact, if you're looking at red, as you are in, say, HA, you're going to have 4 pixels only receiving any light. The green, there are 2 of them compared to the red and the blue. So you could sort of say green, you're a little bit better off, but in reality, you've got quarter of the resolution. So a monochrome camera is going to be exceptionally better, and we could go into debayering and all the rest of it, but basically, if you can, use a monochrome camera, basically is the way to go. All right. So this setup back at that time with that film leaps to that sort of level. So this is with the beta film, the solar continuum filter and monochrome cameras. So that's the 178 there, 178 there, and that's the sort of thing that you can get. That's 2 images stitched together side by side, and again, that's the details of it. That stuff there is the granulation of those convection cells that we're talking about in the layer immediately below the surface, in inverted commas, of the sun. So that's where the plasma underneath is coming up to the surface because it's hot and then cooling down and falling back down. So there's convection cells, and they're the borders of the cells. So that's with the 6SE, with that set up on it that we saw there, and you can see the granulation more clearly. Yep. So what can you see using white light? So you can see the sunspots. So that's a sunspot. Won't go into Wolf numbers and all the rest of it, but you calculate the numbers of sunspots. The umbra the black bit in the middle. If you get your exposure right, you'll notice that it's not fully black. So don't be tempted to process it where you clip that out. It isn't fully black in the middle. Penumbra is this bit going around the edge with the little bits going into it. So, and you can get spots without penumbra, and you can get spots obviously with penumbra. Light bridges, so that's a light bridge. It's sort of trying to form a light bridge. There's a light bridge there. Light bridges are tending to be when the sunspot's going to break up and start to disappear. So if it stays big for longer altogether, all the better. Faculae, we haven't got on that image. That was on the previous image. That's sort of areas of lightness on the surface, and granulation, that's all granulation there. So they're the convection cells. You need a reasonable aperture so to get convection cells. So the 72 ED would be pressed, but the 4 inches perhaps onwards, you're going to get that situation. So that's where we got to with white light. So then we move on to HA. So what is HA? It's an absorption line of hydrogen in the atmosphere, and that's the emission from the sun. So it's pretty narrow, and what you're trying to do is you're trying to look where there's no light. So the photosphere is all this stuff out here, and we're trying to look right down the bottom here where there's the least light, which is a good tip to how to tune your etalons. So we need a filter that fits in that gap there. And if you look at that, this is in angstroms, which is 0.1 of a nanometer. So when you think with your DSO that you've got a 3 nanometer filter and you think you're doing narrowband, think again, okay? It is broader than a bus, a 3 nanometer filter. So we need something really, really narrow. About 1 nanometer is the broadest. If you want to go to half nanometer or way down, into angstroms. So that's what you really need. So that's on band if we can get it slap bang in the middle. So we tune the filter for the histogram to be at its least, because if we're on either side, we're going to get lots more light. This is called the blue wing over this side and the red wing over this side. So we tune to do that. There are some reasons to try and be on other sides for Doppler effects and things like that, but basic tuning, go for your histogram to be at its least. Single stacked, we're talking about at this point there, which will come to what that means. So what do you need to image HA? First of all, you still need an ERF. It can be full aperture, but it doesn't have to be in this case. But you can't put it then, or nor can you do a Herschel wedge going back on reflecting telescopes if you don't have a full aperture ERF, because if you let light into your Cassegrain or your Newtonian stuff, you're going to melt mirror mounts and all sorts of things. So not a recommendation. You also need an etalon, and they can be mounted in all sorts of places, out the front, internally mounted, rear mounted. There are 2 basic types of etalons. They're air-spaced and mica-spaced, and the tuning methods vary a bit about which of the types you're using, and there are a couple of various methods of doing the tuning, which we'll come to in half a second. You need a blocking filter, which will come out in a second for why you need a blocking filter, but basically what comes out of the etalon is more than what you think you're going to get. And so we need to block some extra bits out. And there's also, in most things, another energy rejection filter before coming out to an eyepiece or a camera. So that's in that case there. So an etalon, this is now a narrowband filter. So it's not a coating filter, it's not a dielectric filter. It is an interference filter. So there's an equation. Claire stopped me from having the temptation of putting any maths in here. So there's 2 variables in the equation that you can change though. One is the angle of incidence that the light comes into the etalon. and the other one is the distance between the two partially reflective bits of glass. So it will bounce back and forth at a certain wavelength, and what will come out will be more than just the one wavelength. So that's why we need the blocking filter. This comes out, they call it a comb. Looks like sidebands for electronics type people. So you get a whole stack of things, and we need to have another filter that is narrower than the distance between these, but so it can be much, much wider, so a dielectric filter can do the job. But these two things, so if we change the tilt of the etalon, it changes the frequency or the frequency wavelength of what gets through. So we can tilt tune them, or we can change the distance between them here by pressure tuning. So if we put it in a pressure chamber and squash it together with some air, that will change this, and that'll change the tuning. Or we can put heat in there in the case of the mica ones, so the Daystar and a few other brands, and that will alter that distance slightly, and that will change the tuning. So that's your methods of tuning. Okay, next one of that. So this is our first and the cheapest purchasable HA scope, and probably one of the best value for money. If you look on the internet, the pictures done by the Lunt 40, you'll see some stunning images. So this was our first effort. We still had the color camera at this stage. So that's your etalon. It's on a hinge. That's the hinge. So you tilt it to tune it, and there's a little knob around the other side that is just on a jack thread that does the tilting of it. The objective of the scope is there. It's an f10 scope. It's a helical focuser. The blocking filter is in this diagonal. You can get straights instead of diagonals. This is more for the viewing. So the blocking filter is in there, and the extra energy rejection filter. And at this stage, we were still using our color cameras. So this was our first images that we took with that scope, and they are not falsely colored. They are with the 224 MC or the 178 MC straight through the scope.
And we were pretty excited when we showed these first pictures.
Yeah, we thought pretty happy to see some features around.
Yeah.
Okay, sorry about that.
That's right.
So pretty happy to see that. So our current setup with that same scope, if we were to use it, that's the tuning wheel there. So that's the jack thread, and we've put some little marks on it so we know where we're at. And we've replaced the camera with a monochrome camera. This is a DIY made out of the ZWO one, but the ZWO one puts too much back focus. So that's a tilt adapter. You will need most likely a tilt adapter for narrowband HA, because you get Newton rings in your images, and the only way to get rid of them is to tilt the camera. And on the back of that is a Peltier junction with a heat sink for cooling the camera. They get pretty warm working outside, get to electronics killing type warm, basically. Okay, so that's the sort of, sorry?
Can I just stop you there? We're about to run out of our 40 minutes.
Yep.
So can I let people go to the toilet, have a cup of coffee?
Absolutely.
And
Go for it. Get something good.
Can we resume in, say, at 1:45?
What's the time?
Not a problem.
Beautiful. Okay. Lovely. Thanks for that. Okay. So I'm going to stop the recording now.
Okay.
Okay.
And we'll see you at 1:45 if that's all right. And same link.
Yes,
Yep, cool.
not a problem.
All right. We'll see you then.
Okay. Thanks.
All right.
Okay. Beautiful. Okay, so I'm going to face you around the other way, and off you go. We're not, by the way, sorry, we're not going to do a second, like a third. Okay.
Okay. All right. Host has disabled the screen sharing.
We can't
Have I?
share.
Oh my God.
Yeah.
Hang on a second. There you go.
Go even faster. My goodness. Okay.
No, we can be quick. Just
Yep.
whip through.
No, you're good. You're good.
No.
Okay, we're good to share screen. Okay. Oops, I've gone back one to
We'll go back up one.
Oops, where are we? So they're the
Yes,
Lunt
got it.
40 images with the current day setup. So this is with the monochrome thing and a 1.5 times Barlow in the Lunt 40. So that's what you can get out of a Lunt 40 single stack, which isn't too bad, really. That's just the inverted images of it. So then we went to the idea of doing double stacking, and we bought this scope. We never ever bought the scope to use on its own because we knew that it was a bodgy scope. So if you're tossing up whether you should buy this scope over the Lunt 40,
Go the Lunt 40.
go the Lunt 40 by a mile.
Mm.
In their own literature, they say do not run quarks. They should be around F30, and this scope is F15. It's a marketing exercise because it makes it look cheap, and they want you to have, think that you're doing well having 60 mils, but it's not. So just for the completeness of the exercise, we've included some pictures of this scope as sold. With that setup, we don't use it this way. So we took these pictures especially for this only because we'd never done it. So this is the pictures, which you'd agree is less than what you get from the Lunt. From that scope, that's about as good as we can do. This is how a quark works. So the quark has a convergent beam from the objective way out over here somewhere, comes into a Barlow, which is telecentric. So there's a correcting lens here to make this a collimated beam to hit the etalon. Otherwise, you'd have beams hitting at different angles of incidence, which means your etalon would be tuned all over the place. So our idea was to get the quark off this, which is much cheaper than buying a quark separate, but there's no free lunch here. It's got a smaller clear aperture than the genuine quark. So, but it was significantly cheaper. So like $1,600 versus $2,600. And we were going to use this on the Lunt 40 on its own to stop it down to get it up to a decent focal ratio. So if we go for that, so this is what we did. So this is a 3D printed adapter to put the Lunt 40 etalon out the front. That's obviously already a collimated beam coming from the sun. So that's fine. It hits that one, goes through the objective. It's now stopped down to 40, which, oh, by the way, those images of it on its own was stopped down to 40. If you do it at 60, you may as well throw the thing away. You won't find very many images on the web from this thing. So doing that, then we hit the quark and then go to our cameras there. And so we get double stacked. So going quicker. So there's what a double stacked image, somewhat different again from the other.
Basically, you get a lot more contrast.
Yes.
So your filaments stand out more, your spots, you just get more contrast in your image.
Yep. You're making the filter narrower in that original thing that we showed way back.
Yeah, these are two different cameras.
So these are where we were doing it with a 178mm, and we needed a reducer in there, and it was a GSO 0.5 reducer, not a great piece of equipment. And so we've just recently gone to doing it as a 2-panel mosaic with the 174. It doesn't quite fit with the 174 on its own, but you can definitely see that that is an improvement. So that same setup you just saw, but minus the 0.5 reducer and the camera swapped over. Okay, close-up HA. So our next idea was to use that same Lunt 40 and the cheap quark together to do double stacking at the end of a refractor. So this is, that thing on the front is our flat mask. So that's not part of the equation when taking pictures. It was just taking pictures while it's taking flats. There's an adapter, 3D printed adapter here to take the quark. The quark's there. And now we've got, after the telecentric beam goes through the quark, it stays telecentric. So the back focal distance isn't, it's like a power mate. You can have a lot length there. So it goes through the 40 mil etalon inside a housing here, 3D printed housing, goes out there to the tilt adapter, to the camera, all the rest of the same. And this is being guided. So there's a white light filter there to a normal guide scope being used for guiding, because once you start getting focal ratios like this, it helps to keep things in the frame all the time.
particularly if you're wanting to take flats afterwards, it keeps everything
Yep.
in the same field of
And
view.
animations. Yeah.
Yeah.
Okay. That's just to show what that, so what's that it's all connected to. So that comes back, we'll come back to this bit of equipment in a minute. So there's a separate notebook there that's running K-stars, which positions the mount, and it also has a copy of ASICAP, which is our capture software that is guiding the mount. So you can guide on a disc there. So you just choose the sun on the guide camera and that guides it. That is what the 174 does out of that thing. So that's how much you get. So the 2 panels to make up the whole thing. So that's the capture computer, which is this thing down here, which will come to fast computer. And that's just a tablet. So you can see the gong sight to make sure you've orientated your image the correct way around. So that's what everything's connected to. Okay, keep going. So this is the images you can get double stacked. This is nice.
So yeah,
Surges and bits and pieces, and
yeah,
we could go through what's there in those images, but
yeah,
time's pressing, so we'll keep
Yep.
going through. So they're different images that all from that basic setup that you just saw, and that's if you capture a time lapse over a period of time. So that was probably an hour, and you can do batch capturing with ASICAP or fire capture, and then you stack all of the ones individually and take the best frames. Okay, keep going. So what can you see in the chromosphere with HA? So you can see the active regions, so an active region there. You can see plage, which is
all the white stuff.
all the
basically,
white stuff.
which is basically the chromosphere version of the faculae. So as it comes up.
Next, filaments. So everything that's here, that's these dark lines, is a filament. It's the same thing as these things, only we call them prominences when they go over the edge. So that thing would look like that side on, and filoproms are just a term used for when a prom runs up and over the edge and out. So that's sort of filoprom. There's not a particularly good filoprom in that image, but anyway. And flares, so that's flaring. So if you capture bright things, you can pick up flares at all different time. Spicules you can't see in the previous images. You could see spicules, so they are things you see on the edge, and fibrils are spicules when they're on the flat. So these two are very similar to those two, in as much as when they're on the face, they're one thing, and then when they're on the edge, they're called something different, just to be confusing. So this same scope that we were using before, by the way, that's just an achromatic airspace doublet scope, nothing special, because you're only focusing one wavelength. So you don't need your apochromatics and all the rest of it to do one single wavelength.
Cheap and cheerful.
Cheap and cheerful, exactly. $700 for the scope for that, so pretty cheap. So this has got a white light filter on the front. Now that is not the N5.0. This is 3.8. So you definitely don't put your eye to the other side of this thing, but that's 3.8 beta film. And all the etalons are gone. There's just a spacer there. There's an ERF in here, which is just an IR cut filter, IR UV cut filter. Then there's a ×5 Barlow here, and in this case, there's the solar continuum filter on the front end of the camera, and that can then do your white light. So we saw white light before. This is more what we do with white light now. So probably arguably better again, and you've got granulation, you've got the same sort of stuff in white light that we saw before, but just done differently. But that's what we'd use now. Barlow, we manufactured out of a GSO ×5, and it actually works out to be 4.6 by the time it's been done around without mucking around with it. Okay, yep. With that exact same setup, take the 540 nanometer filter out and put a 393 nanometer, and that is a 3 nanometer wide filter. So it is not a calcium K filter in inverted commas, because it's as broad as, but it's sort of the poor person's version of it, probably as far as we're going to spend money on it. But that gives you a quasi-calcium looking sort of disc. So you're getting a lot more plage slash faculae coming through on what would otherwise look like photosphere sort of details of the spots. So that's what we do presently now. All right. Process for acquisition. So seeing is the determining factor. Aperture does not rule. Well, getting more aperture in this game is a severe waste of money.
Unless you live in the Swiss Alps or something.
Yeah, so
like
right. The person that wrote that book sent a picture of their backyard, and let's just say it doesn't look like our backyard. And his backyard's higher than anywhere in Australia. So going to Kosciuszko might help. So otherwise, focus is always a must, as is in everything with astronomy. Can be hard to do if you've got the light box and the blanket trick.
Well, if you're sitting outside, I mean, it's easier for us because we've got ourselves inside in a position that we can see our monitor, and we've got at least a fighting chance.
Yep.
But if you're sitting outside and you've got your thing over your head and everything, it can be really difficult.
And you need a moment of good seeing to actually get your focus right. If the seeing's bad, focusing is really
difficult. Yeah.
Rotate the camera to orientate the sun north up, which is just a nice touch to do. You want the fastest USB 3 transfer possible. So that's why we use a desktop computer to get the most grunt at the cheapest price. And that computer has the fastest SSD that you can buy in it, because you want to download. You're going to have gigabytes and gigabytes of data compared to what you do. So 300-400 gig, maybe more. Plenty of people shoot a couple of terabytes. So you want fast capture, and you want your camera running fast. So a solid state drive, not an external one. So it needs to be an internal one, definitely a solid state drive. 8 bits is all you need, and that'll be quicker. Again, we didn't go through color cameras and everything, but 8 bits, raw files, but 8 bits will give you a faster thing than 16 bits because you're sending half the number of bytes. So all good. But longer focal lengths guiding is helpful, and particularly for time lapses, which you saw there. So that's a go. And flats for HA. Etalons are not uniform across them, so you really do need to have flats. That was a big step forward when we started doing that, so that's a good thing to have. Okay, so seeing is everything. If the people who've, DSO, it's all about, accumulated time, and you keep all of the images. In this case, it's seeing, and all of the non-man-made things that cause bad seeing is the sun. What are we trying to take pictures of? The sun. So contrary to what you would think of trying to shoot at the zenith, you're better to shoot first thing in the morning before any heat's got there. So you're shooting through the maximum atmosphere, but it's not turbulent yet. Devices to help you doing that. A scintillation monitor really does make a big difference. You were able to buy these things, but if you're half good at it, even moderate electronics kits, you can make one of your own, which is what we did. So that's the Airy Lab one you can buy. Our one, I think we'll have a picture of that in a second. Medio Blue is an interesting site to see for seeing. If you're not looked at seeing before, it gives you a seeing index, and it gives you seeing in arc seconds. So if you do think about wanting big apertures, so our 6-inch aperture is 0.77 of an arc second. You look on there and you ever find a day when that is at 0.77 an arc second, it's hallelujah. It's the best thing that you've ever seen. Over in the Swiss Alps, yes, they have sub-arc second seeing. We never see it. And, if we get 2 arc seconds, we're pretty happy. And these seeing indexes, and obviously you want the jet stream to be as low as possible. So anyone who's done planetary will be on board with what we're talking about there. And basically you need to get just 1 or 2 good images out of it all. Okay, let's go. Local effects. Unlike planetary, however, seeing is really affected by local effects. So people actually spray water on the ground out in front of where their scope is to try and cool things down. Try not to shoot over bricks.
Yeah, if you have, a grassed area in front of you is better than concrete area. Anywhere that's creating heat is in the local environment is an issue.
Shoot over water.
Yeah,
Yep.
so there's
all the things there. If you can do that, that will make a huge difference. And you can see it if you've got the scintillation meter running and you see the arc seconds go down, you'll see the screen suddenly go beautifully clear to see for a very short length of time.
Okay.
There's a graph there's our scintillation meter. So it's just for those people an Arduino, the code, you don't have to write, it's free. You just program the Arduino, and the only thing in that box is a op amp to amplify the signal coming in from this little photo diode, and all the code's done for you. That's a typical graph, and you can see there's 1 arc second. There no sub 1 arc second seeing, and this was a good day. So we got an average of about 2.5. And so what you're trying to do is have really, really fast exposure times to try and get as many frames in these low points as you possibly can.
And try and avoid
and don't press the record button up here.
Yeah.
At 7 arc seconds. You could have a 10 millimeter scope and you'd have too much aperture. Okay. This is a little thing. So there is a formula for the airy disk. So if you work out the aperture for your thing, so in 2 arc seconds, if you have 393 nanometers, the ideal aperture is 49 millimeters, 540 is 68 millimeters, and 656 is 83 millimeter scope. And 2 arc seconds is good. This graph you can see is basically 3 arc seconds. So, a 50 millimeter scope is more than what you can ever use. There's a very smart person who advises on one of the solar forums and says, before you buy a scope, get one of these scintillation meters, run it for a couple of months at home, and then work out what the maximum aperture is and save yourself the money. So it's a very wise person, that one, I can tell you. Lucky imaging, those people who've done planetary know what that is. So highest frames per second possible. You want to have your a short time to capture because the things are changing on the sun very quickly. So 10 seconds,
10 to 15 seconds.
10 to 15 seconds of capture. The shortest possible exposure possible, less than 10 milliseconds. There's maths behind that. There was a paper written in the UK. Less than 10 milliseconds will cut through the turbulence to the best. So you want to quickest possible time. Can't always do it. Take many videos, stack the lot, and then compare the quality figures. If you're not, AutoStack it has an AS3 file that has the quality figures. Take the one with the lowest figure as the best. The highest quality figure. Sorry, beg your pardon. Yep. All right, going too quick. Sharpen all of the stacks and then visually compare to confirm the quality values. Sometimes, for some odd reason, the highest quality number doesn't necessarily give you the best image. We call this lucky imaging. So if you do lots of videos and you choose the best one.
Best video and then...
Yeah. If you're in good place, if you're in the Swiss Alps, you wouldn't have to do this and you could just do one video and take the lucky image. Okay, so processing, AutoStack at 3 is pretty much the go-to program by everyone for stacking them. Make sure that if you've got color files there, that you've got your, if you're using a color camera, that you've got your debayering selected correctly, or otherwise you're going to get a very mucked up thing. And don't have color there if it's monochrome. So make sure it has detected as a monochrome image. Due to the high signal to noise ratio, you're not doing the deep sky stuff where you're stacking images to get your signal to noise ratio. You've got the strongest signal this side of the black stump, so you don't need to worry about being good signal. So you are very, very choosy. Stack 30 frames, maybe even less frames out of thousands of frames. If you add more than those, you'll just add blurriness. And we've done heaps and heaps of tests, and we sort of standardize around 30 frames. But after that, you're just making it worse. add flats for HA. So we take the flats and add them with AutoStack it. If you're using fire capture, you can do the flats on the fly capture, but then you can't not have them there. So yeah, it's a bit of a problem, that one, but yeah, your choice. Batch processing is possible using AutoStack it. So
which is a boon if you take with the lucky imaging when you're taking lots of videos, being able to to batch process them through is
we won't have time to go through how to set up AutoStack it, but yeah, it's if you can do it, look online. There's tutorials. Okay. Processing the sharpening. So for HA images, IMPPG with deconvolution or unsharpened mask is often used. One of the reasons for that is you can do batch sharpening, which is fantastic. Registacks is the sort of go-to for wavelet sharpening. It's a very long in the tooth program, and we are just playing around now with WaveSharp, which is a replacement program. But for our white light images, Registacks and still for HA, but it doesn't have batch processing. WaveSharp does, the new one, so it's the way to go. Suppress the temptation to over sharpen and create artifacts that aren't really there. Again, planetary people will know that temptation all too well. Final processing, we use GIMP. Most people use Photoshop, rotate, clip, stretch, adjust levels, those sorts of things. Add a time and date, and the north is a good idea. Colorize to suit what you want to do for coloring, and that's it, isn't it? That's it, done. Sure. How did we go, Kelly? Were we in time?
No, you did really good. Does anyone have any questions?
Yeah, I'm interested in taking flats. The process of taking flats for HA.
You'll need to translate the question because that was just garbled. So,
sorry.
Interested in how you take your flats for your HA.
Okay. So if we go back to those things where the let's go back quite a bit. Doesn't matter. We'll get there. There we are. No, that's the one before. So the HA flats is that screen there. So that's just 2 layers of the premium Woolworths veggie bag that you get there.
Just the plastic bags.
With an elastic band over a 3D printed thing and whack that on the front of it. Okay. And don't defocus. You just put it on the front of the thing and just
set your histogram till you get a basically a flat sort of view on your screen, so that so it's sort of centered on your histogram, and we take what I can't hear you. Sorry, you need to have the computer turned towards you.
This is while you're still focused on the sun?
Yes.
Yeah. So this is still...
so you just walk straight out, put this straight on top of it, and all you do is change your exposure from milliseconds to seconds. So you'll have a 2-second.
So you basically, wherever you were last taking your image, so whether it's a full disc or a close-up, that's the same. You want to take your flats in exactly the same spot. Yep. So you don't move the scope or anything. You just go out, you put your flats mask on, you take your flats. We take about 30 frames just as an image, a PNG image. And you can take those into AutoStack it, and that it has an area for creating a master flat.
Yep.
And then you apply that master flat to your stacking as it goes through, and it'll automatically put that in for you.
Yep. So we just got one of these 3D printed up for each scope with the premium quality.
Yeah.
That would be one of the cheapest Astro bits you can get, because you get it from Woolworths.
Free with your carrots.
Guides off the
Yep. So the question was about guiding. Are you guiding off the disc?
Yes. So if you've got planets, if you use fire capture, or in our case AsiCap, because in Linux we get better transfer rates with AsiCap, but fire capture is very popular. There's an option to guide off a planet or a disc. So you just simply put that there. So there's a ST4 cable that coming out of the back of the camera into the mount. and this is just the camera lead going back to the computer. So you just have fire capture. It's got to be a separate instance. You can't do it off the one that you're actually capturing off, because this thing's going in, 10 milliseconds, and this thing you don't need to be going like that for guiding. So this is just a normal guide thing.
So we run the guide camera off a separate computer.
Yeah, you could do it all off the one computer with a second instance of your capture software running, but you're possibly going to interfere with getting down as many images as you can for your primary capture.
There are like more expensive type of solar guiding setups that you can buy, nodes and stuff, but they're very expensive. But if you've already got like a guide scope,
that's actually a finder scope. So that's laser cut ply things and a 3D printed thing to take off the back of a normal finder scope and just bung a camera in the back of it
and put your film on the front. That's
very cheap, 50 mil guide scope,
and it works really well.
Yep.
You control all your cameras, and what temperature do you keep it at?
The cameras, these Peltiers would keep it cooler if you put a fan on the back of it, but it does induce vibration even with mounts. There are some people that are using phone coolers, so you can get mobile phone coolers that do it better. So this just knocks it off and stops it. It would go over 50 degrees, which, a lot of electronics is only rated to 50 degrees.
It generally stays, I think it's about 37, 38. I'd have to look at my notes, but I normally keep a check of where it's at. It doesn't, we keep it it's in the 30 degree sort of range.
It heats up because of taking video. You're taking lots and lots of video. When you go to take the flash, you'll see the temperature come down, and then you go back taking video again. And the 174, which is a very popular solar camera, gets much hotter than the 178. So not sure why. But the Peltier junction makes a difference. In winter, don't need it, but in summer.
But it does, that Peltier junction just static like that. It's knocked about 5 to 10 degrees off it, probably. Yeah. So it has helped.
But you're not doing it for like your DSO stuff again. You're doing it to save your camera. You're not doing it because you're getting your noise down. Noise is not an issue with such signal. It's just to stop you cooking your camera. You don't want to be buying a new camera every 2 years or something like that, or every year for that matter. So it's damn hot running electronics at 50 degrees.
Thanks very much. We really appreciate your time. It was a fantastic talk. I love the technical details that you went into. The images are just gorgeous. And thank you so much for taking the time to share what you do with us. We really appreciate it.
Not a problem.
Thank
Our
you.
pleasure.
Thank you.
Thanks.
Okay, and hopefully we'll see you back at the club sometime soon.
Okie dokie.
We'll see how we go.
All right. We've just got to stop breaking arms. That's a good starting point.
That would help.
Of the slides.
Oh, sorry. Peter's asked if we can get a copy of your slides.
Yeah, I can just make them as a PDF and send it to you. Yeah.
Yep, that'd be wonderful. Thank you so much for that. Okay, and like I said, hopefully we'll see you soon.
Yeah, no worries.
Thank you. You too.
Yeah,
Bye.
enjoy.
Bye.